Hello students, welcome to this lecture. In the previous lecture, we discussed about the principles and postulates of quantum mechanics, and in this lecture, we would start looking at some exactly solvable models in quantum chemistry. The first problem that we are going to discuss is the so-called particle in a box problem. The particle in a box problem is quite a relevant problem in chemistry. You can imagine it by considering if the electron is confined to the nuclear environment. So, it is essentially behaving like a particle in a box, where the box is the molecular environment and the particle is an electron. Now, if the electron experiences an infinitely high potential barrier to escape this box, that means to escape this molecular environment, in that case we say that we normally define our potential in this manner, where this is the x axis which goes from minus infinity to plus infinity. The electron or the particle experiences a potential of 0, that means it does not experience any potential energy within the box, within this 0 and L. So, we call this box. Outside, so less than 0 and greater than L, the particle experiences an infinitely high potential. That means it can never escape this box region. So, in that case, if we want to solve this quantum mechanically, the first step is to write down the corresponding Schrodinger equation, and to do that we require the definition of the Hamiltonian operator. So, whenever we deal with any problem quantum mechanically, we have to first step is often we have to write down the corresponding operator, the Hamiltonian operator. In this case, typically in all of the cases, you would see that Hamiltonian operator will have a kinetic energy contribution and some potential energy contribution. Who can contribute to kinetic energy? Whenever we have a particle which has got a mass which is moving with some velocity, so that would have a kinetic energy. In this situation, we have got a particle, a single particle. So, therefore, it has got, let us say, consider its mass is m. So, it has got a kinetic energy. So, you have to write down the kinetic energy operator. Quantum mechanics tells us how to write kinetic energy operator. It is simply p square by 2m, and we know the quantum mechanical definition of operator, the linear momentum operator p. When you do this, we get the kinetic energy operator as shown here, plus the potential energy. What is the potential energy? In the system, if whatever the particle experiences, if there is external field, or if there are other particles with it with which it can interact, in those kind of interactions can be incorporated in this potential energy operator. So, together the kinetic energy and potential energy operators constitute the Hamiltonian operator. In this case, we have the particle in a box problem, where outside the box the potential is infinite and inside the box potential is 0. So, V takes very simple form, is either infinite or does not exist. Now, if I write down the Hamiltonian over here, then I can write down the corresponding Schrodinger equation over there. Now, if you write this down, I am sure you have already solved it in your first quantum mechanics lecture. So, you would see that I would end up in getting a second order homogeneous differential equation, and its solution is pretty straightforward. We are not going to do the solution of this particle in a box, rather we are going to use the results, that means the eigenvalues, that is energies, and the wave functions. So, you know this, the energy is comes out as n square h square divided by 8 ml square, where mass m is the mass of the particle, L is the length of the box, h is the Planck's constant, and this n would be something interesting to discuss, is that when I solve this problem quantum mechanically, when I solve this differential equation, I would find that there are n number of possible solutions. Corresponding to each solution, I get an eigenvalue and I get an eigenfunction. So, these eigenvalues and eigenfunctions have this parameter n that we call the quantum number, and the values of n goes from 1, 2, 3 and so on and so forth. So, before we come to the wave function, let us first discuss about the eigenvalues. So, En, the eigenvalues or the energy depend on some constants, because mass and length of the box are constants for a particular problem. H is anyway universal constant. So, therefore, it has dependence on n square. As n increases from 1, 2, 3, 4, you see the En value goes as n square multiplied by some constant factor for a particular system. Now, the energy spacing keeps on increasing as we go further. The other thing, important thing you see is how the energy depends on the mass and the length of the box. When the mass is very large or the length is very large, then you see the En value becomes very small. When En itself becomes very small, the spacing between En becomes even smaller, right? So that means when mass and length scales are very large, the spacing between two neighboring energy value becomes negligibly small. So much so that this quantized nature of these energy levels disappears. What does that mean? That means when mass is large, length scale is very large, we are actually entering classical realm. In classical world, there is no such quantization of energy level. It is a phenomenon that is starkly observed in quantum world. So therefore, there is a quantum to classical correspondence, a quantum to classical transition as we go for large mass and large length. So that means as we enter classical world, the classical mechanics takes effect. So that means the energy separates, the quantization of energy level disappears. So this is something that comes out from this energy expression. Similarly, the wave function, this factor 2 by L is the normalization constant. You see that we have to, since the wave function has a probabilistic interpretation, psi star psi has a probabilistic interpretation. So it was essential that we could normalize the wave function. So when you normalize the wave function, we get this 2 by L, L is the length of the box under square root, that is actually the normalization constant. Apart from that, you see a sine function. Sine function depends on pi, x and L. X is the dimension of the problem, L is the length of the box, and n is again the quantum number which keeps changing. So now you see the wave functions for different values of n are plotted. You essentially would observe that as I go higher values of n, I am trying to fit more and more number of periods of the sine function into the same length of the box. So as you see, as I go higher in energy level, I start to see more number of places where the wave function becomes 0. For example, here, 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 or in this case here and here. So these places where the wave function becomes 0 are called nodes, because that's where the probability of finding the system becomes 0. So as I go higher in energy level, I see more and more number of nodes. So this is a common feature that you would see in most quantum mechanical systems. Higher energy states typically correspond to more number of nodes. Now, in addition to psi, what you see in the right hand side is the psi star psi, the probability distribution of the corresponding wave eigenfunction. So as you see that, of course, these functions in the left hand side have been squared, so there is no negative and positive. So you can see the places where the wave function vanishes. These are the places of nodes, and these are the places where the particle is most likely to be found. As you go higher and higher, you would see that more and more number of periods are getting confined into the same length of the box. So this result is very easily obtained by solving the differential equation within the box, and outside the box, since the potential is V is infinitely large outside the box, so therefore the particle can never go out. So outside the box, the wave function is always 0. But that makes sense because the particle never escapes the box. So therefore the probability outside is 0. If psi star psi is 0, the wave function is 0. So it makes sense. But that is true only when we have infinitely high wall. But if we have finite barrier, there is a chance of leaking of the wave function or the tunneling. So where you would also see that the wave function slowly decays outside the box. So that is again a pure quantum mechanical phenomena. And when there is a free particle, there is no boundary for it. So, there is no box actually, it is a free particle. Then we get an oscillatory solution all over the space. But this solution that I am showing you here are the quantum mechanical solution of particle trapped in a infinitely high barrier. All right. Now, let us look at another exactly solvable model, which is rather similar in the sense the form of the operator, but it also gives us some other interesting features. This example is the harmonic oscillators. In chemistry, we can use harmonic oscillator in many cases. In general, harmonic oscillator problem is can be considered wherever the system oscillates between oscillates around an equilibrium position. So, if you have a system and you do something to it and then it starts oscillating forward and backward around this equilibrium, the original position or the equilibrium position, that is a typical case where we can use harmonic oscillator problem. In chemistry, where can we use? For example, if we consider bond vibration, we know that when we do IR spectroscopy, for example, we know that equilibrium bond distance. But then we also know in the finite temperature, the system undergoes normal modes of vibration. So, this is essentially that the system shows a harmonic oscillator kind, harmonic movement around the equilibrium position, both marginally stretching, marginally shrinking, and this motion keeps on happening. So, therefore, the molecular vibration is a popular place where harmonic oscillator results are used. In fact, we explain infrared spectroscopy or vibrational spectroscopy by using the eigenfunctions and the eigenvalues of harmonic oscillator problem. Now, harmonic oscillator, so you see here the particle at this point, the particle is at equilibrium position. This is the x-axis along which the particle, the system goes around its equilibrium position. It can be towards positive side or towards negative side. So, the potential is given as a harmonic oscillator potential, which is given as half k x square, where k is the force constant corresponding to that and the harmonic oscillator. We can also express that V, the potential energy, as half m omega square, because omega is the angular frequency, and there is a relation between k and omega that you are aware of. Now, looking at the Hamiltonian, as I said, it would always have a kinetic energy contribution, it would have a potential energy contribution. The potential energy we establish, the kinetic energy is again simple, because what? We have got a particle with a particular mass m, so it has got corresponding kinetic energy operator. So, you would see that the kinetic energy operator in this harmonic oscillator is similar to what we have, what we had for the particle in a box, but the potential is very different. Here in harmonic oscillator, we have a very soft potential, it slowly increases. In case of particle in a box, it is a very hard potential, it is either 0 or infinite, nothing in between. Here in harmonic oscillator, the potential is a soft potential, unlike the particle in a box. Now, if we have this Hamiltonian, the next step is to write down the Schrodinger equation, which is h phi equals E phi, where the phi is an eigenfunction and E is the corresponding eigenvalue. The solution of harmonic oscillator is perhaps little more complicated than particle in a box problem, but nevertheless it is rather straightforward and very much doable. We are not going to again do the derivation to get to the results, but what we are going to do is that we are going to use the final results, that is the energies and the wave function. Let us first consider the energies. The eigenvalues show En depends on this h bar, which is a constant, multiplied by omega. Omega is the frequency corresponding to this harmonic oscillator. So, it depends on the particular system. If you have a harmonic oscillator with very large value of omega, this will get reflected in its energy spectrum. If you have small omega, that also would get reflected. Apart from this, what is interesting is this n plus half factor. This n plus half says that for different values of n, my energy would keep changing. Unlike particle in a box where the minimum value, the lowest allowed value was n equals 1, here the inharmonic oscillator case, the lowest value allowed quantum number is n equals 0. When n equals 0, the corresponding energy is half h bar omega. This energy is called the 0 point energy. That is the energy of the lowest state, which is actually not 0, but that means even when the system is in its ground state, it still has got some energy, and that energy is the 0 point energy. In this case, it is half h bar omega. Now, as I go on for higher values of n equals 1, the energy will be 3 half h bar omega. For n equals 2, that will be 5 half h bar omega. But the separation between two consecutive energy levels is going to be h bar omega. And this separation between two consecutive energy level or h bar omega is actually the IR frequency that we obtain in the IR spectrum, the 0 to n equals 0 to n equals 1 transition. So, that h bar omega is the IR band that we see in infrared spectroscopy, a vibrational spectroscopy. So, the energy spectrum looks like this, but one thing you remember, that harmonic oscillator is always bound. That means no matter how much you stretch this from the equilibrium position, either either right hand side or left hand side, the harmonic potential remains harmonic, because its form is simply half kx square. So, that means it is a very elastic spring, that it simply can go on, we can keep on stretching it or keep on shrinking it, but in real life the harmonic oscillator is a severe approximation. So, we incorporate anharmonicity. I am sure you must have encountered this in your spectroscopy course. So, this is about the eigenvalue. Now, let us consider the eigenfunctions. The eigenfunctions of harmonic oscillator are slightly more complicated than the harmonic eigenfunction of particle in a box. Here, before we introduce the eigen functions, there is something very useful that one uses, is converting this x, which is actually the displacement from the equilibrium position, how much you are going in either direction. One typically expresses into a dimensionless coordinate called rho. Dimensionless coordinate is obtained when you multiply this x with this prefactor m omega divided by h bar. You see, m is the mass of the harmonic oscillator, omega is the corresponding frequency, h bar is a constant. So, based on the m and omega value, you will have a different prefactor which you can multiply to x and obtain this dimensionless coordinate. Normally, the eigenfunctions are expressed in dimensionless coordinates, so that you can switch from one molecular system to another molecular system and the expression remains same, because the effect of the molecular environment gets incorporated by this m omega term. Now, let us look at this wave function little closely, the phi n. The eigenfunction has got three parts. The first one is a n, which is the normalization constant. In a particle in a box problem, the normalization constant was simply 2 by L under square root, did not depend on n, but here the normalization constant depends on the value of n. So, for different value of n, you have a different normalization constant, but it has a standard formula, you see. The second term is the so called Hermite polynomials. What is Hermite polynomial? It is a very useful mathematical polynomial which is very popular in mathematics, always found in most of the textbooks in the appendix. What this Hermite polynomial is like, if you have if you are expressing this polynomial as a function of rho, the Hermite polynomial has the form for different order. So, the 0th order Hermite polynomial is simply 1, the first order Hermite polynomial is 2x or 2 rho, here the rho is the coordinate, and second order and third order are given here. So, the harmonic oscillator wave functions depend on this Hermite polynomials. We will come back to their effect. Third component of this harmonic oscillator eigenfunction is this Gaussian function e to the power minus rho square by 2. Rho is again the dimensionless coordinate. So, there are essentially three features: one, the normalization constant, the Hermite polynomial, and this Gaussian function. Now, if I plot this wave function for different values of n, this is what I am going to get for n equals 0, n equals 1, n equals 2, n equals 3 and so on and so forth. One thing that you would observe that in the eigenfunction, e to the power minus rho square by 2 is a common thing for all of them, and this is anyway an even function. If you look at this Hermite polynomial, you see that Hermite polynomial of order n has each Hermite polynomial has actually got a definite parity. So, if n is even, the Hermite polynomial is even. If n is odd, the corresponding Hermite polynomial of that order is also an odd function. So, you see that this is an odd function, this is an even function, this is an odd function. So, therefore, the eigenfunction of harmonic oscillator is either an even function with respect to rho or an odd function. So, it has got definite parity, and this is very useful in obtaining the properties of this harmonic oscillator. Other thing that you notice that as you go higher, n equals 1, 2, 3, you start seeing more number of places where the wave function becomes 0. In fact, every larger value of n, you would see one more node getting introduced. N equals 1, you have got n equals 1, you have got no node. N equals, sorry, this is n equals 0, you have got no nodes. N equals 1, you have got one node. N equals 2, you have got two nodes, and so on. When I plot the psi star psi, or the probability density that is given as phi n mod square, I get this. Of course, you can understand now this negative and positive have become both positive. One important thing that you notice is that as I go higher and higher, the probability of this wave function gets built up towards the sides, or towards the boundary region of this harmonic oscillator. Mind you, the harmonic oscillator's potential you can imagine to be plotted somewhere here. So, you can see that the probability of finding the system becomes higher at the side regions towards the end of this region, which are also called the turning point regions. That means where the oscillator retraces its path and comes back to the equilibrium to follow the opposite side of the trajectory, and then again from it experiences a turning point and then retraces its path and comes to the again the in the other direction. So, this to and fro motion is restricted by two boundary region, that the turning points. So, at those turning points we see the probability getting accumulated. So, this is again an important concept that we often use in electronic transition, or the spectroscopic discussion, where we talk about vibronic transition, which vibrational state gets maximum intensity. This also contributes to the Frank-Condon factor. So, these are some of the salient features of harmonic oscillator problem. Now, before we go further looking for some the results of exactly solvable models, let us take a pause and start looking at a very important operator and its eigenfunction. This operator is the angular momentum operator. Where do we need angular momentum operator? You see, whenever a particle, for example, in case of particle in a box or in a harmonic oscillator, the movement or the motion of this particle was in linear scale, in one dimension. But suppose imagine if a particle makes a circular motion. So, in that case, the linear momentum does not represent the complete picture. In those cases where the particle shows such circular motion, motion along a circular pathway, in that case we take shelter to the other momentum operator, that is angular momentum. From classical mechanics, we know that angular momentum is given by the cross product of r vector and the linear momentum vector. When the particle is moving around a circle of radius r, so we have r cross p gives us the angular momentum. Now, we know that when we are talking about the results of quantum mechanical results corresponding to a particular operator, we must write down the operator. So, we can write L as a cross of r into p, cross product of r and p vectors. In that case, we would obtain the three Cartesian components of the L operator, that is Lx, Ly, Lz. So, you see they are described in terms of y p z minus z p y. In this slide, the operators are shown without any hat. Of course, you know that the operators are typically shown in hat, but it is also sometimes clear that these are operators, and every time a hat would actually make the slide slightly more complicated to read. So, that is why these are all operators, but without hat. So, Lx, Ly, Lz are there. In addition to individual Cartesian components, we also define the so called L square as this way. In plus, there are two additional operators, L plus and L minus. They are called the step up, step down operator, which are described as the positive and negative combination of Lx and Ly, but in this case Lx is the real dimension, Ly is in the imaginary dimension. So, therefore, L plus and L minus are take complex form of operator. So, these are some of the angular momentum operators. So, these are the definition of the angular momentum, so to speak. Now, whenever we say angular momentum operators, they are usually characterized by this very interesting commutation relation. The three Cartesian components of the angular momentum operator, that is their Lx, Ly, Lz, they do not commute with each other. That means Lx, Ly, they do not commute with each other because their commutation is not 0, rather it is IH bar Lz. Similarly, Ly, Lz, Lz, Lx, they also do not commute with each other. So, Lx, Ly, Lz, they do not commute with each other. Why is it important? This is important because if two operators commute, we know that they can have common eigenfunction. But if they do not commute, then we know that they cannot have common eigenfunctions. So, that means if I know Lx, the outcome of Lx operator for a particular system, I cannot know that for Ly because Lx and Ly, they do not commute. So, the system cannot be, we cannot know the outcome of both the operators simultaneously and precisely. So, that means there will be some uncertainty. So, apart from this the commutation relation, we also have another set of commutation relation, that is how these individual components Lx, Ly, Lz, they commute with L square operator. So, L square Lx, L square Ly, L square Lz, they commute with each other. Now, we have this interesting situation where Lx, Ly, Lz, they do not commute with each other, but each of these components commute with L square. So, that means if we pick up one of these pairs L square and Lz, we just conventionally do that, but we could also pick up L square Ly, L square Lx, does not matter. But if we pick up L square and Lz, then we can see that we can construct simultaneous eigenfunction of this operator, of these two set of operators. So, that is, we can find out the eigenfunctions corresponding to L square operator. So, if I say I have this operator psi, wave eigenfunction psi, so it can be eigenfunction operator L square and it also can be eigenfunction of operator Lz. So, the solution of angular momentum operator, or the eigenfunctions of the angular momentum operator are known are obtained as a common complete set of solution for L square and Lz. So, that means L square and one of these three components. What are they and what are their properties? These are some of the things that we would discuss in our next class. Thank you for your attention.